Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Networked Intelligence at the Robert Bosch Center for Cyber Physical Systems ISC. Today's talk is by Dr. Achintya Kundu, and he will be speaking on robustness and personalization in federated learning. Dr. Achintya is a research scientist at IBM Research, Singapore. Recently, he finished his PhD from the Department of Computer Science and Automation at ISC, Bangalore. He got his ME degree and was the gold medalist from the same institute. Broadly, his research focuses on optimization aspects of machine learning. His current research interest includes federated learning, neural architecture search, primal dual splitting, and momentum-based accelerated algorithms for optimization. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk. And for questions, you may ask Dr. Achintya directly or type them in the chat box and we'll moderate it with him. Over to you, Dr. Achintya.
Thank you. Thanks for the generous introduction. It's a pleasure to, talk to the ISC audience again, this time from Singapore. So I would like the talk to be interactive. So at any point of time, if you have any questions, we can take it. And in the first half of the talk will go a little slow so that if you're not familiar with some of the basics, we can talk in details. So this is the work that I did over the last 1.5 years in IBM. And there are like a few team members. As and when we come to the proposed approaches, we'll talk about that. So let's get into the basics first. Okay, let me share the full screen. Yeah. So I have divided the talk into 4 parts. First, we'll talk about the basic federated learning setup, and then the 2 different aspects of it, robustness and personalization. And finally, we'll discuss about our proposed approach, which integrates both robustness as well as personalization. So what is federated learning? So federated learning actually became very popular last few years. You can see the first paper came out in 2017. So this is a method of training models in a distributed way. There are certain constraints. For example, this is not exactly the distributed computing that we generally talk about in machine learning. Here, the main concern is the data for each of the clients are private, and you cannot share the data, and also you cannot communicate very often to the server, things like that. So let's talk about the setup we are looking at. For example, let's say we have several hospitals. They have their medical images, and they want to learn a classifier which suitably classifies the medical images, so that they can take actions on the medical conditions. Now, each hospital might have a different set of medical images. Their data distribution might be different, and also they might not have sufficient data to train a full-fledged model. So in that setting, what they can do is several hospitals can come together and form a federation. There will be one server which will actually coordinate across these hospitals, but the server will not have access to the private data of these hospitals. So the form of communication will be very minimal. And in that setting, how we can efficiently learn, that's the objective of federated learning. So in mathematical terms, let's define certain things. So we have K clients. That means we have K data sets privately owned, and each one of them wants to actually learn a model. And for example, we have the training data set of client one is given by pairs of XY examples. There are in one of them. And then in a standard setting, if a client has these, N1 samples, they can define the training loss over those samples and try to optimize the particular FK. So the K client's data defines the loss function for the client K, and then it can optimize over that. But that's not the goal here. The goal here is, if we pull together all the training objectives and then try to learn a model which actually is trying to optimize across the data sets that are privately owned. So you are trying to come up with a single model which might work across these data sets. So that's the federated learning objective originally defined. Things have changed from there, and we'll talk about that. So another example of federated learning is, for example, we have mobile phones, and most of the apps actually collect data, and the amount of data might be very little. So it's not sufficient to learn a personalized model for the user. So across the federation, there'll be like several users. If they can collaborate and try to come up with a federated learning kind of setup, then it is possible to learn a meaningful model, because there will be like thousands, millions of mobile phone users who can contribute to this federated learning objective. The only problem is each of these devices or mobile phones, they may not be always present, they may not always communicate, or they may not always participate. So these are the constraints that we have in federated learning. So you cannot always assume that these clients are available and they will update you, in a timely manner. So let's look at the first algorithm that this paper proposed, which is known as a federated averaging algorithm. We call it Fed average. So the setup here is the aggregator or the server initialize a model, and then at any particular time instant, there will be only a subset of the clients are available for computing, the model. So it actually chooses a subset of clients denoted by ST, and then for each of these clients, it sends that model, the aggregator, and then what the clients do is actually take that model, start with that, and then try to optimize its own objective. So let's go back. So the client K has objective defined over only its own data set. So it can only optimize over that. So once it gets a model, for example, W tilde T from the server, it starts its optimization process, initialize with that model, and then try to optimize the FK loss function. So this is given by this client update state. So it actually initializes, and then the optimization can be done through stochastic gradient descent. That means you compute the gradient over a bunch of samples and then do a gradient descent. And once you do a certain amount of computation, like for example, quite a few number of passes over your data set, then you can send your updated model to the server. So, and similarly, other clients also will do the same thing. Once the server receives the updated models from the clients, it has to somehow combine the models to get a the updated global model which will work across the data sets. So in the standard algorithm, the aggregation function is just the weighted averaging. The weight can be decided by the amount of data that each of the clients have. So this A function is just it takes the client's updated model and does a something like taking the mean of them to compute the global model. So this is the basic algorithm where there are flexibility. For example, the client side can do any kind of optimization it wants to do. There is no control over it. So, for example, a client might, not, return a properly updated model. It can as well return a junk model, or a, try to act as an adversary, try to fool the other, models. So things like that can happen. So the goal here is, to overcome things like that, and also utilize that the clients can do a certain amount of computation. So utilize that to, minimize the amount of communication that you need. Like, for example, if all the clients are doing several iterations before sending the updated model, then you expect that, okay, in quite a few number of rounds of communication, you can converge to a good global model. So at this point, I'd like to, take few questions if the setup is not clear, because we'll build up on this basic setup where, the aggregator actually tries to combine the models given by the client, and the client actually, after taking the model from the server, tries to optimize on its own data set. So this is the basic setup we have. Any questions? Am I audible properly?
Yes.
Okay. So hopefully the basic setup is clear. Now let's look at some of the problems that
Dr. Achintya,
yeah.
there is a question from Zubair.
Yeah.
So the question is, what is the model? Is it like some classifier?
Yes. So in this case, it can be a classifier or a regression problem, because what we defined was a supervised learning setup, right? So it can be done for unsupervised learning as well, but let's keep it simple. So we are looking at a supervised learning setup where we have training samples. It can be for binary classification, multi-class classification, or regression, all of these. So, and by model, you can say whether it is a logistic regression model for classification, or, a deep neural network for classification. It can be anything of that. But the model is same across all the, clients that are participating. So they want to try, learn is the exact same model, only the model parameters that are variable here. So once you fix a model, that then you want to learn those model parameters. We are talking about learning those model parameters by denoting them as W. So for all these, for the whole of the talk, you can assume that we are trying to learn a binary classifier, and the classifier model is the logistic regression. So that means it's defined by a weight vector, which is given by this W. But it can, it's the same procedure, whether it's a deep neural net or, supervector machine. It is, valid for training any kind of models in a supervised manner. So certain aspects are, important. For example, as I mentioned, that the global model is generally taken as an average of the client model. So in certain spaces, for example, if you are talking about the discrete models like random forest or decision trees, for them it will not work as it is, because there is no averaging operations of the model parameters. So certain restrictions are there, but in general, where we have continuous model parameters, where by taking average or things like that, we get a perfectly valid model, then this will work. Any other questions? Okay, so let's move forward. So there are certain things, as I mentioned, that the server updates the model by taking average of the client models. If some of the clients are, acting as adversaries, then it will definitely fail because the mean aggregation function is very prone to outliers. A second option is, where it can fail is we have variety of, data sets, right? So, for example, if you are looking at the mobile phone space, certain users' data might be very different from other users. So there is a, if you just take average, then the whole thing might be, uh, you know, what do you say? If we take average, then it may not be very meaningful because certain users' data might be heavily biased. So how do we, compute this aggregation in a robust way from the local models? So that is the question of robustness. And also, it also will deal with the kind of adversarial attacks that we are thinking. So if some of the clients are acting as adversaries, it will also take care of that. Another challenge in that setting will be, even if we use a robust aggregation of the client models, for example, some robust ways of estimating the mean, then under those conditions, can we ensure that the federated learning procedure will converge? So these are the questions that we have. So let's look at one approach which came out in 2019. It proposes geometric median as a method of aggregating the client models. How it does, it optimizes something like this. So you have WKs, which are the client models. Then it tries to find W, which is close to each one of them in a two-norm sense. So this is the way geometric median is defined. And it is known that it is very robust. Even if you arbitrarily corrupt half of the data points, still you will get a very good estimation of the mean. So under this, they tried to prove the convergence of the federated averaging algorithm, and there are other ways of aggregating, robust ways of aggregating the client models. Another example here is the coordinate-wise median. So instead of taking geometric median, which is a little computationally intensive, coordinate-wise median is very easy to calculate because when you are doing coordinate-wise, you can just sort the values and then find the median. So it's as simple as that, but it can be written as an optimization problem like this. There is another robust aggregation function known as coordinate-wise trimmed mean. So since you are doing coordinate-wise, you can get the set of values, and then you do an ordering, and you trim them. By that, I mean, like, you remove the 20% smaller values and the 20% the largest values, and then you compute the mean of the remaining one. So that will also give you a robust robust way of, again, calculating the mean. And there are so using these robust aggregation methods, they have tried to also prove the convergence of the federated learning approach. But the problem with the existing approach is based on the
Achintya,
yeah
sorry to interrupt.
yeah
Can I ask a question? Nilesh here.
right
So in the coordinate-wise trimmed mean that you mentioned,
yes.
so how do they define robustness, and like how do they show it's better, for example, than not trimming? Like,
So I'm not aware of how, how much robustness it provides, but this paper actually using this coordinate-wise trimmed mean as an as a measure of robust aggregation, they try to prove convergence. So it will of course depend on how much you are trimming. It will depend on that. So maybe you can go through the paper. So here our focus is not on what should be the method of aggregation, but given a method of aggregation, how do we ensure that the federated learning algorithm will converge? So you may be aware of, like, there are many ways of estimating the mean from the robust point of view. So so this is maybe one such, which is easy to deal with when you are trying to prove convergence. So that's what I can comment. Yeah, so we can look into the details of it. So main issue here is proving convergence using the robust aggregation methods, not about proving the robustness of this aggregation method.
All right, thanks.
Yeah. So I mean, there are many other ways of doing robust aggregation. So for this talk, actually, this coordinate-wise median and geometric median will do. Okay. So the problem here I mentioned, based on the robust aggregation method you employ, you have to derive your convergence results, in a very specific way. There is no generic structure that is available. So this is one thing that we want to actually explore. That even if you employ like different robust aggregation function, still your federated learning approach should work. So now let us look at some of the assumptions in the original federated learning setup. So we saw that the first assumption is the the training samples in a particular data sets are IID. This is fairly common assumption in machine learning, which is okay for us. The second assumption is more critical here, because we are working across clients, and this is where the assumption will fail, because the data sets of different users, different clients, different mobile phones, or different hospitals definitely going to be different. And we cannot just optimize one particular model which will work across the data sets. So there are work in that direction, how to come up with better federated learning setup where we can actually do better on the individual data sets. So that brings us to the aspect of personalization. So one single model might not be a good idea to work with multiple data sets. So if we can personalize a model for a particular data set, that might be better. So towards that, one paper came up in 2020. So this actually doesn't talk about personalizing the model for a particular data set, but what actually it tries to avoid, even if you don't have the IID data setting, still your algorithm should converge and provide satisfactory performance. To do that, the changes that they made, if you remember, original federated averaging algorithm just applied stochastic gradient descent on the private data set of the client K. And because these clients can have different data sets, and that might actually lead to the failure of the algorithm, because different data sets, you are still doing model averaging, then you might not reach anywhere. So instead of doing that, the Fed prox approach actually proposed something very standard in machine learning, which is you just regularize the client's local data set objective by the global model that actually is given by the server. So basically, if you see this optimization objective looks like, you want to minimize, you want to find a model which minimizes your loss on your particular data set K, but you also want to be very close to the global model that was sent by the server. So this actually solves some of the convergence issues which arises because of the non-IID-ness of the data. But here we are still learning a single global model which should work across the board. So let's formulate it in a different way. We had the federated learning objective where we are trying to learn a single model which works across the K data sets. Each one gives rise to one of the training objectives denoted as FK. Now we are saying that, okay, if we have k different models, each for each of the client, and we write it in a different manner, that okay, all the models are the same as the global model. That's what we are trying to do right till now. But now, from the personalized point of view, what we will be looking at is this constraint WK is equals to W tilde. The client side's local model should not be equal to the global model. That's what we will look at. So basically, we'll relax at this constraint. So one particular method that came up recently was this method called DITO, where they first learn a global model, as in federated averaging. You can employ robust aggregation as well. So it doesn't talk about anything how you want to learn the global model. Once you learn the global model, then you use a something like the FedProx. You use it for a quadratic regularizer. And then try to find a personalized model. So another method which came up recently is this method called personalized federated learning with Morio envelopes. So here, if you see the training objective, originally we had FKs, right? Sorry, there is a K missing here. So originally we had FKs, but here the paper actually proposes that you don't have to optimize over the training loss defined by its own data set. You actually use something like an approximation, which is given by this Morio envelope. So capital FK is an approximation of the original loss function FK, and you try to find a global model which optimizes over those approximate loss functions. And once you do that, then you can always find a local model by regularizing it. So this is the local model computation part, and the global model computation is as it is, but based on the capital FKs. So the problem here is, now since you have defined an approximation of the original loss function, you have to compute gradient of that. And this makes it little computationally heavy. You have to run a separate loop to compute the gradient of FK. Another federated learning approach where they wants to have a client-specific model is this method called adaptive personalized federated learning, where they want to learn models which are a combination of the global model given by W tilde and also a local version of it, and taking a convex combination of these two. So with this convex combination weight also can be learned, and they have formulated the objective as follows, where they are learning the VKs, which are the local part, and the W tilde, which is the global part, both simultaneously. So this is also computationally heavy because you have to compute the gradient with respect to both of these model parameters and update these. Any comments on the personalized approaches? Is it clear?
Yeah, hi, Samar is here.
Yeah.
So the question is, like, how is it different from the transfer learning? Because there also you have a model, then you would like you take that model and then
Right.
you train it based on the personal data.
Right. So so here we don't have any model to start with. So all we are just having a bunch of data sets privately owned. So there is no so in transfer learning, you always transfer from one particular model which is already trained, right?
Mm-hmm.
So we have to. So what we are talking about is you first together learn something. For example, the global model itself. Once you know the global model, then you can always transfer it to your local model, do something like the transfer learning kind of thing. But the global model itself is not known, and how do we actually train this global model? If you just train based on what we already saw, which is like optimizing over the full. So if you look at this problem here, we are learning a single model, which is the global model, which optimizes across all the FKs, right? this itself might fail in the first place because the data sets are not homogeneous or IID. So we have to take into the account the personalization aspect beforehand, even before training the global model. So once you have the global model, then we can talk about transfer learning. But here we don't have any trained model before. So, so federated learning is about training personalized model from the scratch. We don't have anything. Only thing we want to get benefited from the collaboration, because the other data sets are also trying to learn their personalized models, and they might be very similar. So we'll come to that point now.
Okay, so
yes.
follow-up question. So initially, when your centralized or parameters server
right.
distributes the model, it's an empty model. Is it
right? It's just randomly initialized.
Okay. Thanks.
Yeah.
Hi, Nilesh here. Just one question in this last thing you showed.
Yeah.
What prevents alpha k and vk essentially from converging to the natural choice, which is alpha k is 0 and then vk becomes, or actually no, just vk becomes w tilde? Like, what is preventing that from happening? Like, why is personalization happening here?
Yeah, so I'm not particularly favoring this model. So this is one model which was proposed in that. So their idea is to have ideally if you know how much to balance between your global and the personalized aspect. For example, let's say that okay, mostly I'll be very close to the global model, but maybe 10% weightage I want to put so that my VKs, which are like may not be aligned with W tilde, so you put a very small weightage towards that. But the paper also suggests that okay, if you don't know the prior weighting or if you don't have any knowledge, then you can also learn this through optimization. In that case, it becomes a very non-convex optimization problem, as you can see. So I'm not sure what prevents it from going to 0 and 1. In our experience, actually, we have seen things like that happening. Either it is going, I think mostly it is going to 0 in a lot of cases that we have seen. But the paper actually doesn't give any insight when it should go to 0 or to 1.
Thanks.
Yeah. So there is no guiding principle how you should define your personalized model. So that brings us to our proposed approach, which actually recently got published in IEEE Edge conference. And here we have tried to work on both the aspect, the robustness as well as personalization. If I make a comment, in all these personalized approaches, there is no robustness involved. That means the server is still doing averaging, and their convergence result is based on only the averaging. So this is joint work with 3 other IBM employees here. Okay, so this is how we formulate our personalized federated learning problem. So we have seen that okay, there are like k data sets, and they give rise to the loss function fk. We want to learn a personalized model wk for that data set. Now we also want to get benefited from the collaboration. That means we expect that okay, the data sets across the federation, there is a lot of overlap. It's not a right word to use. What I mean is like a lot of knowledge that you can gain for training your personalized model. So to incorporate that, what we actually say that this personalized model is a combination of 2 parts: the global model, and then there is a personalized part theta k. This theta k is actually regularized. So there is no regularization on the W tilde, but theta k is heavily regularized, so that you don't want to deviate too much from the global model. So and this is where actually the robustness comes in. You can employ robust regularizers one norm, two norm. The squared Euclidean norm actually is not going to give you robustness, but the other two, one norm and two norm, will give. So this is the formulation that we want to actually solve. So here we have the personalized models, which is composed of two parts: the global model plus a personalized component, and the personalized component actually has a regularization component. So basically, if the regulation is too high, for example, if you look at the first one, it's 0 if and only if it is 0, otherwise it's infinity. That will enforce that, okay, you cannot deviate from the global model. So it's actually basically the original problem itself, that you want to learn a single model across all the data sets. So whereas other regularizers will allow you to deviate from the global model, and based on the amount of regulation you employ, you'll get your results. So here we are not specifying what regularizer you should use. You are free to use your own favorite regularizer. Maybe on certain components you want to use one norm, on certain components you define a two norm. You are completely given flexibility of choosing this regularizer. Now with that, this problem is still very difficult to solve because of this hard constraint, hard equality constraint. So what we do is we replace this hard constraint using a penalty. So this is the penalty. So this ensures that this is the way we modeled it, WK as W tilde plus theta K, is somewhat close. Now, this actually has several benefits. If you look at the WK, and once you fix the W tilde and theta K, then optimizing over WK is very simple, which we look at here. So the clients actually tries to optimize over WK. It doesn't care. It gets all the information like theta K and W tilde from the server, whereas the server actually tries to optimize the theta K and W tilde for the whole federation to work. So this is a completely alternating minimization based approach. And what actually benefits this has is when you do alternating minimization, at every iteration you are trying to actually go down in the objective function value. So the convergence is not an issue here. So even with a generic function like psi, we are always guaranteed to minimize the objective function value. So is this formulation clear?
So,
okay, so yeah.
Sorry, Nilesh, again about this personalization. So
Yeah.
I get it that different users would have effectively different Ws.
Yes,
so I
yes.
see to it that I do see that it's different for different users. But
Yes.
what I don't follow is whatever W I get, how do I know it's personalized? I mean, like it is indeed what I want and not something else altogether. I mean, this notion of personalization, just the way it's being discussed, it seems like it's just different for different users. But how do I know it's personalized?
Oh yeah, I see. So first of all, by personalized here, we mean that, okay, the WK is triggered to optimize only the objective function FK. So if you remember earlier, we were trying to have one W tilde which is getting optimized across the FKs, right? So here we have a separate optimization variable WK, but then we want to have something which actually is sharing, right? If we just want to, if we don't have the psi theta K, for example, here, then it's just separate optimization problems, right?
Mm-hmm.
So there is nothing you are learning from each other then. So that will be the best case in personalization. Like you have your model which suits your data, but that is not possible. You may not have enough data to have a very good model to train on. On top of that, you might want to benefit from so many other clients that are there. So you need to model this in a fashion that, okay, you have a component which actually will give you flexibility to optimize over your own data set, but it will have another component which actually is trying to learn from all other models. So here our modeling is in terms of this, that it has a big chunk of the W tilde, which is shared across all the data sets. And then we have a personalized component. We want to keep the personalized component, regularized, so that otherwise, if this will just learn a personalized model for each one of them, they may not even, collaborate.
Thanks. Yeah.
Yeah. So in terms of optimization, how do you solve this optimization problem? As I said, it's purely alternating minimization. Once the server sends its parameters like W tilde and theta k, then the client can start optimizing. So what is the optimization problem that the client needs to solve? If you fix theta k and W tilde, then the remaining part becomes just this. So here you see how the personalization is happening. So earlier, if you remember, we had the data space client specific objective FK, and then we wanted to regularize using the global model only. But here there is another term coming into picture, which is a personalized part. So you are not only regularizing with the global model, but each client is regularizing using a different model, which is a combination of the global model and a personalized component. So this is where the personalization is coming into picture based on the objective function that we have defined. And now we are free to optimize this objective based on our computational capability. Either we can do full optimization, or we can do several iteration of SGD. This number of iterations are very flexible. That we have already seen in FedProc's approach, that okay, in the original approach, each one of the client has to do a certain number of iterations. It's fixed. Here, since it's a regularized objective, each of the client can do variable number of iterations and then send their updated model. Another important difference that we bring in, if you remember the initialization part, in all other existing methods, they just start with the global model and then try to optimize this objective, which is defined over their own data. But here what we do is we don't start with the global model that is given by the server. We always start with what we had previously. For example, last time I sent, let's say, WKT to the server. So I'll start with that because I have that personalized model, which was like over several iterations. I don't want to again start from the global model, which is like same across all the data sets. So this is another innovation that we bring in. And this actually keeps the continuity in the learning, because you are always starting from where you left. And then let's look at the server side, what is happening. So server side, the WKs are frozen because you have got the updated model from the clients. Now you want to find the global model. So you can always do the minimization of over theta k. So if you do the minimization over theta k, this psi function becomes just an approximate version of psi, which is given by Morio and Voloff. It's a smooth version of psi. And now you see that, okay, once you freeze WK, then optimizing over W tilde only involves just the psi cap functions. There's no role of FK. So that means you are completely detached on the server side. So let's look at that. So here we want to optimize that over the W tilde for a fixed set of WKs. And if we do that, we call it the aggregation function. This is defined completely in terms of the psi function that somebody chooses. And earlier, if we recall the definitions of these various measures of aggregation, geometric median, coordinate-wise median, and mean, you see exactly the same kind of structure where the psi cap is replaced by a different norm or the squared norm. So basically, we have somehow come to the same form of robust aggregations, whether it is mean or the geometric median, but through a different route, which, as we saw, incorporates the personalized approach, but also provides these robust ways of aggregating the client models. So let's look at what we get. Since we don't have psi, we have psi cap here. So if we choose these psi functions, then what we get is like some approximate version of this, because the psi cap is a smooth version of psi. And originally geometric median was proposed as a robust aggregation measure for federated learning. In the paper RFA, they also actually computes approximate geometric median, because computing the geometric median is actually a non-smooth problem. Psi is just 2 norm, so it's non-differentiable, whereas psi cap is a smooth version of psi, and it will provide you approximate geometric median. Also, computationally, this is easy to calculate because of the smoothness. And 3 different psi function gives rise to 3 different algorithms from our proposed framework, which we define as Fed Comed plus, Geomed plus, and the Fed average plus. I think we are close to finishing. Yeah. So let's look at some results here. So the setup here is we have the MNIST data set, and it is partitioned into a number of clients, whether it is 10 or 50. And then for each of these clients, what we do is you keep the data set as it is, and for certain clients, the images, you actually do an inversion, like for each pixel, you use the white pixels become black pixels become white. So you take the negative of the image. So certain clients have this adversarial data set now. So under that setting, can we learn meaningfully? So these are the data sets denoted as MNIST R, and we have 2 different settings. In one case, we have 10 different clients, and in another case, we have 50 different clients. And we see that the robust method actually outperforms the other method. Though we have this Fed average plus from our formulation, but it doesn't employ any robust aggregation, as we saw. It only has the mean aggregation, right? So, and then we also test on personalized data set. That means for each of the client, we change the data distribution. What we do, we take the images corresponding to few digits. The MNIST has 0 to 10, 0 to 9, 10 digits. So we randomly take 2 digits, and we add noise to all the images of those digits. So in this setting, actually now the clients have a different data distribution, and that in that case also we see that the robust method actually outperforms all other approaches, even the personalized approaches that are recently proposed. You can look at the more results in our the published version, and if you have any comments, I can take now before concluding.
Yeah, hello, sir.
Yeah.
Sir, in this personalization MNIST, sir, I did not understand, sir, how you distribute the data, sir.
Okay. So
is it like you gave all the zero images to one client, or 1 images to one client and 2 images to third client? Is it like that, or it is like randomly?
Yeah, so the whole data set has images of digits 0 to 9. So you partition the data set equally into 10 different. You equally partition them into 10 different clients. So each one has the IID data as of now, right? After that, once we have this IID set up, each of the client has images of the 10 digits. Now, what we do is for certain clients, we take the inverted image. We change the pixel values. So that makes it a robust setting. That means the certain clients don't have the original images. So it's no longer non-IID setting, it's adversarial setting.
So this P is to P tensor in this.
Yeah. In P, we have, let's say the base setup is the IID. You take a client and then you randomly choose 2 digits and images corresponding to those 2 digits. You add a lot of noise, Laplacian noise. So the distribution of those images will change, right? For a different client, you choose 2 different digits, and then you do the same adding noise. So basically now each of the clients will now have a different data distribution, right? Though they start. So this is how we artificially generate robust and personalized data sets out of any list.
Thanks.
Okay, so in our Fed Plus approach, what we have tried to achieve is we have tried to provide robustness as a way to find personalized model, and also we have tried to be very flexible in terms of providing choices of this regularizer, and that will lead to different regularization function. That will lead to different, personalized variants of the algorithm or different ways of aggregating. So that flexibility is there. But on the plus side, we don't have to worry about the optimization aspect of it. That means the algorithm will definitely converge because it is based on the alternating mediation principle. So this is the benefit of the Fed Plus approach. Any further questions?
Yeah, hi, Somor is here. So, the thing I think you assume that all the users are available in each iteration, right? The global.
No. So, okay, let's go back to the first. Yes. So in the original setup itself, you don't assume that all the users are available. So you always have this a subset ST of the clients, and only those clients will do this update and then send you. The remaining clients, you can say for that round, they are not present. So this is how we do the experimentation. In real scenario, actually the server will not decide which of the clients are active, but the client themselves will be, deciding that. But all our experiments, actually, we only choose a random subset at every round.
Yeah. So based on that, like I would I wanted to know that what is the implication that how many users turn out to contribute in a particular iteration. So is it just the convergence takes a lot of time, or is there are any other applications?
Definitely, the convergence will depend on the fraction of what fraction of clients actually are participating in each round, and also so that will be the one aspect of it. And second aspect of it is, which we have not explored till now, we are not making any assumptions, statistical assumption on the FKs. Let's say the FKs are very similar, the data sets, the data distribution are very similar. So in that case, convergence will definitely be faster, even if like there are like only few clients participating. So from the optimization angle, the more is the client participation, the convergence will be faster. From statistical point of view, the more there is data similarity, if the optimization loss function FKs are very similar, then also it will converge very fast.
Okay, thanks.
But in general, like we assume only, let's say 10 to 20% of the clients are available at any particular round.
Yeah, hello, sir. Hello, sir.
Yeah, I can hear you.
Sir, this update when clients when clients this communicate to the server, does it happen at the same time or like it happens at different times? Sir?
So here we are assuming a synchronous approach. That means once, for simplicity, let's say the server sends its updated global model to all the clients, let's say. Okay,
Yes,
now it's up to the client whether they will work on it or not. So let's say certain clients are active, they take that model W tilde T and then they optimizes over their own data set. Somebody runs 100 iterations, somebody may run 1,000 iterations. And then maybe there is a defined time, okay, that by this time you return the model. So so certain clients, whoever actually returns the model by that time, the server will take those models and aggregate. If somebody comes after that, it is not considered. So this is kind of a synchronous approach.
Okay, so because I was asking because the processing power may be different for different clients, right?
Yes. So in our model, we are not asking each client to do same amount of computation. Whatever computation it can do, so that itself will be beneficial. Yeah.
Okay, thanks.
So that was one actually difference that all these later versions are incorporating. If you see this algorithm here, it is mentioned that each of these clients are doing E iterations on the FK, right? So everybody has to do the fixed number of iterations. This was in the first algorithm, but that has been relaxed in our approach and many other approaches. So you can do variable amount of computation at different clients.
Thank you, Dr. Achintya, for the interesting talk. If there are no more questions, maybe we can close the session. Okay. Thank you once again for being a part of the seminar series. As discussed before, we would like to remind the audience to subscribe to our Google Groups, which is the mailing list for information on future talks. You can also visit our website for more details, and the links have already been pasted in the chat box. The link to the recorded video will be posted on the webpage. Thank you, everyone, and have a great evening.
Thank you.